So we ended last time by defining these two types of discontinuities, and we're going to continue our conversation about discontinuities, and we're going to now look at some examples. But before we do that, let's talk about how are we going to find, if we're just given the algebraic form of f of x, meaning not looking at the graph, how would we be able to find where there are some points of discontinuity? All right, so the first kind of situation we have the same two culprits actually that often cause us issues to make us look more closely when we evaluate limits. Okay, and the first issue when we evaluate limits that we always have to look more closely at has to be values that make the denominator zero. That's always, it's a perpetual issue in math because division by zero isn't defined. So that's going to be the first situation we're going to look for here. So one situation is going to be any values that make a denominator, so essentially you'll be setting your denominator equal to zero. I just started to spell that wrong. So any values that are going to make your denominator equal to zero. Any of these values are going to be discontinuities. So these definitely will be discontinuities. And if you think about why, if you think about your three-part definition, your three-step definition for continuity, it's pretty clear kind of why these are going to be discontinuities. And that's going to be because, we'll just say they'll fail step one in our three-part definition, meaning these are places where the function does not exist. So these, we'll just say f of these values, f of c, we'll just say that, f of c, for whatever these values of c, they won't exist. So these points won't exist. They'll fail the first part of the definition. So let me kind of add, since I started to refer to c here, let's say any values c. Let me squeeze that in up here. So any values, so we'll say any values, and I'll just say c, that make our denominator equal to zero are going to be discontinuities because they will make the denominator division by zero is undefined, and that means f of these values simply will not exist. Now, it's important to realize, and we saw this with our graph that we have up here, so those could either be little holes in the graph, like if you look up above at f of -3, or they could be little removable, or they could be vertical asymptotes. So these could fall under the category of either removable or non-removable. So this is just kind of another thing to sort of note off to the side here. So in terms of values that make your denominator zero, let's just say, let's note that these could either be what I referred to up above as removable. They could either be removable discontinuities, and in particular, we're talking about little like holes in the graph, right? That aren't defined somewhere else, so a little hole in the graph. Or they could also be non-removable. So they could also be non-removable discontinuities, if they're of the type, in particular, they could be vertical asymptotes. So we know that they're going to fail step 1 of the 3-part definition because f of these values won't exist. But that could either mean a little hole in the graph, which could be removable, or it could mean that it's non-removable because it could be a vertical asymptote, meaning the limit still may or may not exist, right? So we would have to investigate that further if we were asked more specifically, like which type we had. All right, then the other thing we're going to always look for, so this is what we do when we're looking for points of discontinuity algebraically. So the second thing we're going to have to look at is we're going to need to, I'm going to say, investigate. We're going to have to investigate what I refer to as those cutoff points in piecewise defined functions. So those points where the function is changing definition. So cutoff points of our piecewise defined functions. And you know, with these, like all bets are off. Anything can happen. They can be continuities, they can be discontinuities, but we don't know. So we are investigating here. So I'll kind of add that in parentheses. So these may or may not be discontinuities. So, you know, piecewise defined functions, really anything can happen here. So what this is going to mean is that we're just going to have to really investigate it carefully with our 3-part definition. So let's just kind of add that as a note off to the side here. So let's just say note, basically anything can happen with piecewise functions. And so because of that, that means we're going to just need to use our 3-step definition. So we will just want to use our 3-step definition in order to do that, you know, investigate what's happening at that point. All right, so this is what we're going to kind of be mindful of, and this is what we're going to be thinking about when we are being asked to try to find our points of discontinuity by hand, essentially. So let's take a look at a couple of examples. All right, so number 1, let's say we have the function f of x is equal to, and let's say we have 2x squared plus 1 if x is less than 0, negative 1 if x is equal to 0, and x plus 1 if x is greater than 0. All right, so let's break this into a few different parts here. So part A, let's just determine if there is any of these discontinuities. And you want to, as you're working on your homework, read the directions carefully. They may say find where the function is continuous. Well, it's still the same exercise. It's looking for any discontinuities and then throwing those out of the continuous answer. So just kind of look on how the actual answer that they're looking for, how they are phrasing that question. All right, so in this situation, we are obviously, we don't have any denominators, but we definitely have ourselves a piecewise defined function. And so we definitely need to just investigate what's happening at x equals 0. So that's what we need to do. So we're simply going to kind of look into, and we want to investigate continuity at x equals 0. And of course, this means we're going to do that with our three-step definition. And then this will also help us yield a different additional information when we're done. So that's exactly what we're going to do here. All right, so the first part of our three-part definition here. All right, so part one, let's first just see, does the point exist? Is it defined? So step number one in our three-part definition with proper math notation says, what is f of 0? And so this is where you're looking for the equality part. This is the pre-calc question. Just if I sub in 0, do I get back something for y? And we do. It's equal to -1. So it passes our first definition. The point is defined. It exists. All right, so now we're going to go on then to step number 2. And so when we're looking here then at step number 2 is going to be about the limit. So we go on to investigate with our proper math notation the limit as x goes to 0 of f of x. But in order to investigate the limit as x approaches a cutoff point of a piecewise function, we have to know to look at the limit from both sides. So we have to know that that requires of me that I look at the limit as x approaches 0 from the left. So let's start with that. So left of 0, so that's going to mean I'm looking at coming in from the left or from the less than side of 0. And so that's going to be according to this first rule here. And so that's going to be my 2 times 0 squared plus 1. That's going to be 1. And then we need to look at the limit as x approaches 0 from the right. So coming from the right of 0, so right of 0, I'm getting values from the larger side of 0. And so that would be coming into 0 plus 1, and so that is also 1. And so because these two are equal, then this is going to imply that my overall limit does exist. The limit as x approaches 0 of f of x is equal to 1. So we pass on step number 2. So the third step then is looking to see whether or not these two results that we just got here, whether or not they're equal. So step number 3 is looking at the result that we got in step 1, f of 0, is that equal to what we were working on in step 2, which was the limit as x approaches 0. And in this situation, these two are not equal to each other. So f of 0 was equal to -1, and the limit as x approaches 0, that was equal to 1. So we have failed our three-part definition here at step number 3. The limit and the points are not equal to each other. Okay, so our final answer here is we would say, so f of x is discontinuous. So we are discontinuous at x equals 0. So we have a discontinuity at x equals 0. All right, now part B, so that was my part A. So for part B, I want us to address whether or not this discontinuity is removable or not. So is this discontinuity, removable? All right, So to determine if it's removable, remember this is the idea of, well, can I remove it by just defining or redefining one point? And that only happens if you kind of look back up. Remember, removable discontinuities, what I have up here at the top in red, only happen if the limit exists. So they are removable if their limit exists, and this one does. The limit as x approaches 0 was equal to 1. So this one is definitely removable. So yes, x equals 0 is a removable discontinuity. And then I'll always want to kind of know why, and that is because the limit as x approaches 0 of f of x exists. So it is removable because the limit exists. Now, a third question that you'll often be asked if you do have a removable discontinuity is going to be to then define or potentially redefine, depending on the context of the problem, redefine f of 0 to make f of x continuous. So if it's removable, I should be able to just define or redefine a point. Well, right now, the point, if we scroll back up, the point was defined at f of 0 was equal to -1, but the limit was at 1. So we simply need to redefine that point at 0. It simply needs to be redefined to equal where the limit exists. So f of 0 would need to be defined at 1. And if it was, if you go back up to your three-part definition, the first part there in blue, if f of 0 is equal to 1, the limit's equal to 1, and the two would be equal. So that's where we would, define that point. All right, so that's a good example of a piecewise function. Let's look at one more example here in this video. Let's look at a function g of x equal to, we're going to do a rational function here, 2x squared minus x minus 1 all over x squared minus 1. And so on this one, we'll phrase our initial question differently, just so we're kind of always paying attention to that. So let's find where g of x is continuous. So we'll want to be careful as we phrase our answer here. So we still need to search for the discontinuities and then just throw those out, essentially, if we're trying to answer where the function is continuous. Well, it's not a piecewise function, but it is a rational function. There is a denominator, so we need to throw out any values that make our denominator 0. So remember, we always have discontinuities. So discontinuities are always going to occur wherever your denominator is equal to 0. So that means x squared minus 1 equal to 0. And then I suppose you have two choices. You can either think about factoring into x plus 1, x minus 1, but it tends to be that I see a lot of students just solve this by adding 1 and taking the square root. And that's fine, but one thing that you have to remember is anytime you're going to take a square root to get rid of the square, in your solving process here, you have to remember to introduce the plus or minus square root on the other side, something that students often forget. So just a little reminder on that. So we end up with plus or minus square root of 1, which is, of course, 1. And so remember, these are the 2 points that we just found. These are our discontinuities. So if we're supposed to state where g of x is continuous, then we would say everywhere except for those two values, but we'd probably write that in interval notation. So we might say g of x is continuous on the interval from negative infinity to negative 1, and then union or comma, kind of that varies from book to book sometimes, negative 1 to 1, and then union or comma 1 to infinity. So remember, this is how you throw out a value in interval notation. You stop an interval at a point with an open parenthesis, and then you pick up the next interval with an open parenthesis. So it's not included in either of those. So we've thrown out just negative 1 and 1. All right, so part B then, I want us to decide, kind of looking at these discontinuities that we just found. Let's decide, are these discontinuities, so we just found 2 of them, right? So are these discontinuities removable or non-removable? But it's easier to say, are they removable or not? Okay, so remember the idea here is that they're removable if their limits exist. So I really just want to investigate the limits as x approaches each of these values here. So let's investigate what's happening at x equals 1 by looking at the limit as x approaches 1 of that function g of x up above. Now initially, if I sub in g of x, and what you might see me do quite a bit on something like this is you might see, I tend to do this, I don't know if I've done it much yet in my videos so far, but if you sub in 1, I get 2 minus 1 minus 1, 0 over 0. So kind of what we're thinking relatively quickly when we try direct substitution is we get 0 over 0, which is an indeterminate form. All right, so that means, based on what we studied in the last section, it's indeterminate. So we are going to try, especially in the case of 2 polynomials like this, we're going to try to do some factoring. And so, yeah, 2x squared, and then that means I'd have to start with a 2x and an x, and then a negative 1 product. Well, that would just have to be 1 and 1, and opposite signs trying to get to that negative 1 sum. So this is just the trial and error approach to factoring. Again, some of you might be more familiar and comfortable with that AC grouping technique. However you factor, you need to be able to factor. All right, so in this situation, I do get a couple of common factors that we are going to reduce, being mindful that I am changing the function at this point. Remember what we talked about? These functions aren't equal, but their limits are equal. And so essentially what I have done here is I've basically filled in what was a little open circle. And so this is going to be removable, but let's finish it out. So let's now evaluate as we sub in our 1. And so we're going to have 2 plus 1, 3 over 1 plus 1 is 2. So this implies, because the limit existed, this is going to tell us that x equals 1 is a removable discontinuity. So this is a removable discontinuity. And again, this is because the limit exists. That's how we know for sure that x equals 1 is a removable discontinuity. And that's the kind of justification I'd want to see. All right, so let's take a look at then x equals negative 1. And so if we were to investigate again the limit as x approaches now negative 1 of g of x up above. Okay, this one though is a little different, because when I sub in negative 1, I would have 2 times negative 1 squared would be 2 times 1, so that would be 2, minus the negative 1 is going to be plus 1, and then minus 1. So my denominator is still going to be negative 1 squared is 1. My denominator is still 0, but my numerator is 2. So first of all, I want you to note that this is not an indeterminate form. And I'm kind of previewing something a little bit and at the same time reviewing something. So you may remember, you kind of think about from pre-calc. So first of all, let me just kind of mention that this right here is not, a little bit of a double negative in my language, this is not indeterminate. Now, you may be thinking, you know what though, I bet I would try to factor anyway. Like I would have factored and reduced just like I did up above. But guess what? The good news is, even if you did, and you were left with 2x plus 1 over x plus 1, and you were to sub in negative 1, you would still get a non-zero number over 0. And it's this non-zero number over 0 that we want to recall from our college algebra or from our pre-calculus days. So what we want to kind of remember, so I'll just put that part in parentheses, we want to recall from pre-calculus, when you probably spent a whole unit in pre-calc or college algebra, values that made denominator 0, like in college algebra, 99% of the time, those were your vertical asymptotes. You didn't encounter very much in pre-calc or college algebra with these little holes in the graph. So most of the time, you were getting non-zero numbers over 0, and these were these values that made your denominator 0, but didn't make your numerator 0. These were your vertical asymptotes. Okay, so from pre-calc, this is, you get a vertical, well, I'll write it out. I tend to abbreviate vertical asymptote, VA. You get a vertical asymptote when, let's say a vertical asymptote at x equals c, when if you sub in f of c, if you get a non-zero number over 0. So it's maybe been a little while since you've thought about that little fact, but we are going to come back to that again very soon. So this is a combination of a remember from before, and also we're going to come back to this later. So what we really have here with this non-zero number over 0 is we have a vertical asymptote situation. So we have a vertical asymptote at x equals negative 1. And so that tells us it's definitely non-removable. So this fact is going to tell us, so x equals negative 1 is a non-removable discontinuity because x equals negative 1 is a vertical asymptote. So we have kind of a lot to unpack in that example. There was a lot going on. It started off pretty simple, just two values that made our denominator 0, and then the algebraic work of deciding if these are removable or not just made us kind of go into this limit, and we have the good old indeterminate form where we factor, reduce, reevaluate, the limit exists. That meant that it was removable. And then the other situation where we get a non-zero number over 0, we're going to see more of that in future sections. A non-zero number over 0 meant that we had a vertical asymptote. So I think we'll kind of end there. When we come back next time, I have a little note about continuity at endpoints, but then we have one more little theorem to end the section with, something called intermediate value theorem. So we'll take a look at that next time.